Hey there, chemists. We've been talking about how to use NMR spectroscopy to identify the structures of compounds. And on this lesson, we're just going to do a little matching exercise to take 6 compounds and match them up with their 6 spectra, which are all on your notes for today. At the top, I've got just a slightly different version of the reference chart for where different types of hydrogens show up in the NMR spectrum. Remember, the more electron-poor types of hydrogens show up way to the left, and more electron-rich hydrogens show off to the right. This is an approximate scale of where they show up. Don't treat these as hard boundaries. It really depends on the molecule, but it gives you a general sense of where they show up. The splitting pattern is very useful. The integration is very useful, and you'll notice that the integration and splitting is given because if we were conducting this on an actual instrument, you'd be able to use the software to get that information for relative integration ratios and hopefully a good resolved splitting pattern. Now, the thing to do first here is just turn these names into actual chemical structures so we can actually look at what they look like. Acetone is the simplest of all ketones. It's just propanone. Right below it, 2,2-dimethoxypropane. That's a propane with 2 O-methyl groups attached to the same central carbon. 1,2-dichloroethane is a 2-carbon chain with a chlorine on the first and second carbon. 1-bromopropane, simple primary bromide. 1,1,2-trichloroethane would look like that. And then 2-bromopropane has this isopropyl group attached to a bromide. So now we can actually look at the structures and try to decide which one is which. How to approach this? There's a couple of different ways. They're all valid. Notice off the bat we have these are actual spectra. These are not ChemDraw predicted spectra like we were using in the previous lesson. So they have a reference peak of what's called tetramethyl silane. That is just a reference, tetramethyl silane. It's one of many different reference compounds that chemists use just to set and calibrate where the scale is. We've defined this to be at a 0 part per million on the scale, and everything else is relative to that. But what that means is it's not part of the molecule. So we are not going to look at that when we're considering what the molecule actually looks like. Okay, so let's approach this by looking at each spectrum and trying to identify which compound it could be. The first one only has one signal, and it is a singlet. Notice there's no integration because there's nothing else to integrate it relative to. So this has to be a molecule that only has one type of hydrogen in the same chemical environment, which means it's either the acetone molecule or the dichloroethane molecule, because those two have only one type of hydrogen due to the symmetry in the molecule. You might say, oh, well, it can't possibly be the dichloroethane molecule because the two hydrogens would split their neighbors, but that's not true in this case. When they're all identical, they don't split each other. So both of those compounds would look like a one hydrogen singlet, or just a multi-hydrogen singlet. There's no integration. They would look like a single singlet. So the other thing that helps me is the location. And since we're talking about something with only one signal, I notice that in spectrum D, I also have only one signal. It's the location that's going to tell me which type of hydrogen it is and which molecule it is. Spectrum A has a singlet in the 3s, whereas spectrum D is down in the 2s. So if it's up in the 3s, this is an H on a carbon that's near some X group, where X is maybe an oxygen or a halogen. That's just based on the reference up above. Whereas the location in the 2s for spectrum D, this is an H that would be attached to a carbon which is adjacent to some other carbon that's doubly bonded to something, maybe another carbon or a halogen. And that right there actually narrows down which one is which. So A must be the dichloroethane molecule because there's H's that are on carbons attached to chlorines. And spectrum D must be the acetone molecule. So I'll just draw the structures on top of that, and we can even fill in that A goes with the dichloroethane molecule, and D goes with the acetone. So there's 4 left. Why don't you hit pause and see if you can identify which spectrum goes with which compound of the remaining 4. Okay, if you've done that, let's just go through them one at a time. If we look at spectrum B has 2 signals. The integration is a 1-to-1, or they've actually upped it to 6-to-6, and they're both singlets, so no neighbors. So we need a compound that only has 2 types of hydrogens, one fairly electron rich down in the alkane region, and another one up in the next to an oxygen or halogen region. So we could even label those as alkyl hydrogens, whereas this would be H's next to some electronegative atom like a halogen or an oxygen. And if we look up above, we see plenty of oxygens and halogens in the remaining 4 compounds, but the only one that works for this would be the dimethoxypropane molecule because of the location and the splitting pattern. And once you draw the structure, you can make sense of why this compound is what it is. We've got these 3 hydrogens and these 3 hydrogens both on carbons attached to an oxygen. So they should show up somewhere in the 3s. So it makes sense that they correspond to those 6 hydrogens in that one signal. We've also got 2 other methyl groups down there, but they're far enough away from the oxygen that they don't have that electronic environment, so they're down in the alkyl region, and there's nothing else. So we only have 2 signals. They match up with that. So spectrum B is going to be the dimethoxypropane. Moving on to spectrum C, we have, again, 2 signals. We have a 6-hydrogen doublet. This looks alkyl. And now that we have some splitting, we can guess a little bit more about what the structure looks like. If it's 6 hydrogens, that means it's got a total of 6. There's never going to be 6 on any one carbon, but it could be 2 methyls. Could be 2 methyl groups, 2 CH3s, and because it's a doublet, that means we know that the neighboring carbon, the adjacent carbon, has exactly 1 hydrogen on it. We don't know what else is on that carbon, but this is sort of our little building block that would give rise to this signal, both in terms of the integration and the splitting pattern. In fact, if it's 2 of them, that means it could be 2 methyls on the same carbon. So we could actually draw a second methyl right on it. And that would make sense that that matches exactly what we see in this signal. So we've got 2 methyls, CH3, CH3. That would be a 6-hydrogen signal. And if they're next to another H, that would give rise to the doublet. Speaking of this other H, remember how splitting works. If you see me, then I see you. So this H would be split by the 6 neighbors into a septet. So that's the other signal. So we've already drawn the right piece of the puzzle. This is this 1 hydrogen septet, and then it's just a question of what else is attached to this. Well, looking up the possibilities, the only thing that fits is the 2-bromopropane molecule. So this is 2-bromopropane. We can just highlight in the actual structure where everything is. That 1 hydrogen right there in the middle is the septet, and then the methyls on either end, the doublet. And just to fill in up top, that means C is 2-bromopropane. And then going forward, we've already done spectrum D, so it's just the last 2. Spectrum E also has 2 signals. This one, I notice, has a 1 hydrogen peak and a 2 hydrogen peak. And if you look at the remaining 2 molecules we haven't picked yet, that must be the dichloroethane because it's got the right number of hydrogens. 1-bromopropane has more hydrogens than that. So this spectrum must be the trichloroethane molecule. And for this one, we'll just draw out the hydrogens. We actually saw the tribromo version of this same kind of structure a few lessons ago, and it looks very similar. You've got a single hydrogen right here that's next to 2 halogens, so very electron poor, and as a result, it's split into a triplet because it sees these two neighbors. And likewise, these two neighboring hydrogens integrate for 2. They're next to 1 halogen of chlorine, so up in the 4s roughly, and they're split by this 1 into a doublet. So then we get our 2-hydrogen doublet for that. That must mean that the last one is 1-bromopropane. Let's draw out the structure for 1-bromopropane, and let's go ahead and fill in the H's and make sense of the integration, the splitting, and the location. Starting with the 2 hydrogens that are right next to the bromine, those must be the most electron poor, so those would be this signal right here. Makes sense that it integrates for 2. It's also got 2 neighbors, so it's split into a triplet. Next to that, we've got 2 other H's, which are a little bit farther from the bromine, so not quite as electron poor, and they have a total of 1, 2, 3, 4, 5 neighbors, so the n+1 rule in this case gives us 6, and you get what's called a sextet. So then that would explain the sextet. And then lastly, we have these 3 hydrogens all the way on the end. Those would be the most electron rich. They see the 2 adjacent hydrogens, so it would be split into a triplet and integrate for 3, and then that would explain that triplet right there. So we've been able to match every spectrum with every molecule. We could just write the letters to fill in. This is E, and this is F. And we're slowly working our way into deciphering what a spectrum is and interpreting its structure without a matching exercise. But for now, in the back, there's some good homework problems. Let you do some more matching exercises for NMR spectroscopy.